Lesson 2.2, Polynomial Division. For further review, check out section 2.4 in your textbook. The main topic of this lesson is going to be synthetic division. Students will use synthetic division to divide a polynomial by a polynomial. Some other things that we're going to look at the end of this lesson will have to do with something known as the Remainder Theorem and the Factor Theorem. Students will divide polynomials and relate the result to the Remainder and Factor Theorem. Students will use the Remainder Theorem to determine if x minus a is a factor of a polynomial. So the main goal is going to be synthetic division. How do we divide a polynomial by another polynomial using synthetic division? And then as a result of that, we'll be able to use synthetic division in order to determine if something is a factor using both the Remainder Theorem and the Factor Theorem. But before we get to any of that, I want to take a step back and go to dividing by a monomial. So the main goal of this lesson is going to be dividing a polynomial by a polynomial. Keep in mind, a polynomial can be any number of terms. Technically 3x and x squared, those are polynomials, but because there's only one term, they have a special significance. And when we're dividing by a monomial, we don't need any special techniques. We just need the basic idea of having a common denominator when you're adding or subtracting fractions. Essentially what we have here, 3x cubed plus 5x squared plus 8x minus 9 divided by 3x, is the end result of adding and subtracting fractions together. The common denominator was 3x. Anytime you have a monomial denominator, a single term on the denominator, one option you have available to you is simply to break it up into its constituent fractions, its separate fractions, all with that common denominator. So if I'm dividing the whole thing by 3x, that's the same thing as dividing each individual term by 3x. Essentially what I'm doing here is distribution with division. Remember, multiplication and division are the same. So if I was multiplying this polynomial by 3x, I would distribute 3x times this, 3x times that, 3x times this, 3x times that. But because I'm dividing, I'm just distributing with division. 3x cubed divided by 3x, 5x squared divided by 3x, 8x divided by 3x, negative 9 divided by 3x. So essentially, I'm done with the division part. Now, if there's anything that I can simplify, I need to simplify. For instance, 3 over 3, that's going to cancel out. X cubed over x to the first, well, the x here and one of the x's here is going to cancel out. 5 over 3, nothing happens there. X squared over x, well, the x cancels, and then one of the x's here cancels, leaving just one behind. 8 over 3, nothing happens. X and x are going to cancel out. Now in this case, looking at the variables first, I don't have any variables up top, so that x is going to stay put. And then 9 over 3 is 3. Now because the answer is 3 and not 1 over 3, the 3 would be left on the top. So I end up with a final answer of x squared plus 5/3 x plus 8/3 minus 3 over x. Here's another one. Try this one on your own. Hit play when you're ready. So same basic deal. We're going to split it up into however many fractions we have based on the number of terms on the top. 4 terms on the top, 1 term on the bottom. That means 4 fractions overall, all over x squared. Looking at one fraction at a time, 4 doesn't cancel with anything. X cubed and x squared, that's going to leave a single x behind. 3 doesn't cancel with anything, but the x squareds completely cancel out. 4 doesn't cancel with anything. I've got 1x on the top, I've got 2 x's on the bottom, so 1x cancels on the top, 1x cancels on the bottom, leaving 1 behind, and then nothing cancels on this term, so I would be left with 4x minus 3 minus 4 over x plus 3 over x squared. Now before we get into the main focus of this lesson, polynomial division using synthetic division, I want to take a step all the way back to elementary school and look at the long division algorithm. And then we're going to go step by step and see how that old long division algorithm actually leads us directly into our more advanced algebraic technique known as synthetic division. So 347 divided by 2. Hopefully you remember how to do this long division algorithm. If you don't remember how to do the long division algorithm, that's nice. Not the focus of this course. Just follow along as best you can. When I'm doing my long division algorithm, I'll set up my division bar. Remember that the inside is what number's on top, and the outside is the number that's on the bottom. In more fancy language, this top number would be the dividend, and the bottom number would be the divisor. So I'll put the 2 on the outside, 347 on the inside, and then I'll start my algorithm, one step at a time. Starting with the 2, I'll ask myself, how many times does 2 go into 3? Hopefully you agree that the answer is clearly 1. So then that number will go up here, and then I will multiply this number times this number, and I'll stick it right underneath the 3. Then my last step of the algorithm is to subtract, and I get 1. Now I'm going to repeat this algorithm until I run out of terms completely. I'm done with the 3. Now let's move the 4 down, and instead of looking to see how many times the 2 goes into 3, now it's 2 into 14. 2 goes into 14 7 times. Multiply and subtract. This time I get 0. Doesn't really matter what numbers you get during the process. What matters is that you finish the process. I still have one more number, so let's bring that on down. 2 goes into 7 3 times. 3 times 2 gives us 6. Subtract, we get 1. Now since I've run out of terms, I can't go any further, so that 1 is called a remainder. Now of course there is another option here where I could go ahead and start putting in decimal points, 0.0000, and keep going until I actually do get a whole number answer, if a whole number answer is possible. But that's again not the focus of this lesson, so we're not going to look at that situation here. I want to look at situations where I stop when I get to a remainder. So what do I do with that remainder? I know the answer of 347 divided by 2 is 173 and a remainder of 1, but we are better than just saying and there's a remainder of 1. As we increase our mathematical knowledge and mathematical understanding, we need to know the proper way to present information. And one of the beautiful things about mathematics is that there's always more than one way to look at any given problem. The division algorithm is one way to get to the answer to this division question. But another way to get to the answer would be simply fraction manipulation, if you want to call it that. 347, would you agree, is the same thing as 346 plus 1. Now, the only reason I knew to break off that plus 1 is because I had already done this problem and I knew there was a remainder of 1, but I'm just wanting to show that I can get the answer a different way using a different method. Now, thinking about the couple of examples that we just did, I have a monomial denominator, which means I can break this into two fractions, 346 over 2 plus 1 over 2. Now 1 over 2 I can't do anything with, but 346 over 2, that's an even number divided by 2. I can definitely simplify this. The way I would do this in my head real quick is to say, well, I know that 3 can't be cut in half, but 34, half of 34 is 17, and then half of 6 is 3. Therefore, 346 divided by 2 is 173 plus 1 half. Now notice, my remainder using the long division was 1. My answer when I did my fraction manipulation had a 1 half left over. That 1 right there is the same thing as that 1 right there. In other words, the remainder is the numerator of a remaining fraction. So when I get a remainder using the long division algorithm, what I'm going to do is I'm going to stick that remainder as a fraction attached to the end of the quotient. Remember that the answer to a division problem is called a quotient. So it's the quotient plus the remainder divided by the original divisor, which was 2. If you think about it, that makes sense because the remainder is that which was unable to be divided, thus it should still be over 2. So to summarize that real quick, anytime you're doing a division problem where you have a dividend divided by a divisor, the answer is the quotient plus the remainder over the original divisor. So whatever you get as your remainder, stick that over whatever the original divisor was as a fraction attached to the end. Now let's go back to a algebra problem, dividing a polynomial by a polynomial using the long division algorithm. Again, the focus of this lesson is synthetic division. We are building up to synthetic division. In the future, you will only ever use synthetic division. You may have been told in the past by an algebra teacher that synthetic division only works in certain situations, otherwise you have to use long division. I am here to tell you that that is a lie. That is a lie that algebra teachers tell you in order to force you to learn how to do long division. But now that we are beyond that basic algebra class, you have earned the right to use exclusively synthetic division, but you have to be careful because those situations where a previous algebra teacher may have told you that synthetic division won't work, technically they were right because synthetic division alone won't work. There is some sort of adjustment that you have to make based on those situations, which we will talk about when we get to it. But Before we get to it, I want to talk about the long division algorithm and how that leads to the synthetic division algorithm. So consider dividing by a binomial. Notice we are dividing by 3x plus 2 instead of just a single term. So breaking this up into separate fractions is not going to help us because I would have 3x cubed over 3x plus 2, 5x squared over 3x plus 2, 8x over 3x plus 2, 7 over 3x plus 2. There's really nothing I could do from that point forward because I have more than just a single term in the denominator. So when I have more than a single term, I need to use some sort of advanced division algorithm. So using my long division algorithm that we just reviewed, I'll set up my division bar. 3x plus 2 goes on the outside, 3x cubed plus 5x squared plus 8x plus 7 goes on the inside. Now, the fun part. The next step would be to ask how many times does the outside go into the first term on the inside. But we need to get a little creative in how we do this. Instead of looking at the entire outside, I'm just going to look at the 3x. The question is not how many times does 3x plus 2 go into 3x cubed, but just how many times does 3x go into 3x cubed. A much simpler problem. Now, instead of asking it that way though, how many times does 3x go into 3x cubed, I'm going to ask it in the reverse order. 3x cubed divided by 3x is what? Because remember, when I ask how many times does 3x go into 3x cubed, like if I asked how many times does 2 go into 10, the answer would be 5, because what I'm really saying is 2 times what gives us 10. Well, I could have gotten that same answer, how many times does 2 go into 10, by asking what's 10 divided by 2? It's 5. So that's the question I'm going to ask here. How many times does 3x go into 3x cubed is equivalent to saying what's 3x cubed divided by 3x. So 3's would cancel, x cubed over x would be x squared. So how many times does 3x go into 3x cubed? It goes in x squared times. Now notice I put the x squared over the x squared term just to keep my like terms lined up. No other reason, not really required, it's just something I do. So remember, the next step of the algorithm, once I get the number up top, is to multiply. But this time, instead of multiplying just by 3x, I'm going to multiply by the entire outside, 3x plus 2. X squared times 3x gives me 3x cubed. I'll line up my like terms. X squared times 2 is 2x squared. After I multiply, my next step in the algorithm is to subtract. 3x cubed minus 3x cubed is going to disappear completely. 5x squared minus 2x squared is going to be 3x squared. That finishes the first level of the algorithm. Lather, rinse, repeat. I'll bring down the 8x and ask myself how many times does 3x go into 3x squared. Remember, this is the same thing as asking 3x squared divided by 3x. 3's cancel out. X squared divided by x is x. So that goes up top. We'll multiply. X times 3x plus 2 would give me 3x squared plus 2x. Subtract. 3x squared cancels out. 8x minus 2x gives me 6x. Bring down the 7. 3x goes into 6x. Well, that's, again, 6x divided by 3x really is 2. 2 times 3x plus 2 would give me 6x plus 4. Subtract, and I'm left with 3. Since I've run out of terms, I now know that I'm done and that my remainder is 3. So, using my formatting rules that I established a minute ago, I'm going to write my answer as my quotient, x squared plus x plus 2, plus my remainder, 3, over the original divisor, 3x plus 2. So 3x cubed plus 5x squared plus 8x plus 7 over 3x plus 2, which was the original question, is equivalent to x squared plus x plus 2 plus 3 over 3x plus 2, the long division algorithm. Now, if you are a math nerd like me, I encourage you to practice this long division algorithm as much as you feel like practicing it so that you really have it down. But again, for the purposes of this course, you will not be assessed on the long division algorithm. What we will be focusing on is synthetic division. So let's see how this relates to that. Let's use a slightly simpler example, and then we'll come back to the example that we just did a little bit later. So consider 2x cubed minus 3x squared minus 5x minus 12 over x minus 3. As I said before, if you are the math nerd type and you want to go ahead and try this out using long division and see if you get the right answer, feel free to pause the video here, give it a try, and hit play when you're ready, and you'll see if you get the right answer. But for the rest of us, the goal here is not long division. we are focusing on the shortcut to long division known as synthetic division. So I'm just going to jump straight to the answer. 2x squared plus 3x plus 4. There's the what the answer would be if we went through it the long way. Now, what I want to stress upon you is that there are only certain aspects of this long division algorithm that actually are crucial to getting the answer. For instance, one thing I mentioned previously that you may have caught, you may not have caught, is I kept lining up the like terms. As we all know, in algebra, like terms always have to go together. And you've also grown accustomed to listing terms in descending order. For instance, I've got x cubed, then x squared, then x, and then my constant term. What you can do is think of these variable terms, the x cubed, the x squared, the x, and so on, as a place value system. What this is like saying is like, this is my 1000 level, this is my 100 level, this is my 10 level, and this is my ones placed. As long as I list the terms in the right order, then the variables themselves don't need to be there. For instance, when I say 152, you're not going to confuse 152 with 125 because the order of the numbers indicate the value of the numbers. When I say 152, I'm telling you that the 1 represents 100, the 5 represents 50, and the 2 represents just 2. Because of the place of the number. So when I put the terms in order, the cubic term, the quadratic term, the linear term, the constant term, as long as I keep them in order, I can get rid of the variables completely. That 2, that -3, that -5, that -12 still represent the same thing because they're in that particular order. Now, the next thing I could ignore is all these leading terms right here, the 2, the 3, the 4. What you may have noticed as part of the algorithm, let me back up a little bit, when I asked how many times x goes into 2x cubed, we've got 2x squared. But then I immediately took that 2x squared and remultiplied it by x to stick it right here. And then when I subtracted, that leading term always disappeared. And it will always disappear. So if it always disappears, then that leading term really isn't crucial to the process at all. What's crucial is this secondary term, this -6, this -9, this -12. That's what leads me to the next step, to the next step, to the next step, to see what the next term of the answer is actually going to end up being. So, get rid of the variables, get rid of these leading terms so that only the -6, the -9, and the -12 stay behind, and then I'm going to reorganize some things. I took that -6, that -9, that -12, and I moved them all in a line. Notice one more time, -6, -9, -12 moved up here, and then the 2, 3, and 4, which were part of the quotient, I went ahead and put those downstairs. Also remember that the algorithm called for taking the numbers up top and multiplying by the number of outside in order to get to the next level. That's still happening up here. 2 times -3 gives us -6. 3 times -3 gives us -9. 4 times -3 gives us -12. We also subtracted vertically to get from one term to the next. Now 2, there's nothing here. 2 minus 0 is 2. -3 minus -6 gives us +3. -5 minus -9 gives us +4. -12 minus -12 gives us 0. But that all double negative stuff gets a little cumbersome. The reason these negatives are even here is because of this negative out here. If I, instead of doing 3 times -3, if I did 3 times +3, that would make this a +6. It would actually make all these numbers positive. So what we actually do is we get rid of the negative out here, and instead of subtracting, we're going to add vertically. 2 plus 0 gives us 2. 2 times 3 gives us 6. -3 plus 6 gives us 3. 3 times 3 gives us 9, and so on and so forth. So to recap, we start by putting the number outside. Now this number outside that 3, remember it originally came from the divisor of x minus 3, which makes +3 the root of the divisor. Whatever you're dividing by, find the root of that number, put it on the outside. 2, -3, -5, and -12, those are the coefficients of the dividend, just the numbers of the inside. We're then always going to add vertically instead of subtracting. Now we are adding. That's really the only major difference between the long division and the synthetic division algorithm. You add vertically instead of subtracting. And once we have our number downstairs, we're still going to do the same thing we did before. We're going to multiply by the outside. So the 2 plus nothing gives me 2. So basically we can always just take that number and drop it straight down. 2 times 3 gives us 6, and add. 3 times 3 gives us 9, and add. 4 times 3 gives us 12, and add. Whatever that last number is represents your remainder. And then the 2, the 3, and the 4 would represent the coefficients of the quotient. So we started with 2x cubed. When we divided, we would end up with 2x squared plus 3x plus 4. And then that would be your final answer. So the idea with synthetic division is take the variables out in order to figure out the numbers that represent your answer, and then put the variables back in order to present your answer. So let's look at this example together, just so that we go through one problem all the way from beginning to end, and then you can try the next one on your own. So what I see here is a polynomial division problem. I have more than a single term on the bottom, so I'm not just going to split this up. I'm going to use a division algorithm. Long division or synthetic division would work. Obviously, I'm going to pick synthetic division. So I'm going to start by setting up my basic structure. The divisor is going to go out here, and then the dividend is going to go inside. The way I actually figure out the number that goes on the outside is I'm going to look at the divisor, x plus 3. I'm going to find the root. Set it equal to 0. I get negative 3. So negative 3 will go on the outside, and then the coefficients of the dividend will go on the inside. Now we have to be careful. Look at this very closely. Do you notice anything that's missing? Hopefully you notice that there's an x cubed term missing. I've got x to the 4th, and then I've got x squared. There should be an x cubed in here. This is the difference between 104 and 14. If I just tell you 1/4, you're going to assume I mean 14. But if I'm wanting to imply that it's 104, then I have to put a placeholder in the tens position, such as the 0 between the 1 and the 4, in order to signify to the reader that I don't mean 14, I mean 104. So it's the same thing here. I'm missing x cubed, which means when I get to that point in the process, the coefficient of x to the 4th is 1, the coefficient of x to the 3rd, since x to the 3rd is missing, I'm going to use a placeholder, 0. Anytime you're missing a term, put in a 0 as a placeholder. So I've got 1x to the 4th, 0x cubed, negative 10x squared, negative 2x plus 4. Rule of thumb, look at the degree of the polynomial. If it's 4th degree, then you should have 5 coefficients. If it's 20th degree, you should have 21 coefficients. Remember, because the last term doesn't have a variable, you're always going to have one extra term than the leading degree. So my setup is all done. Now let's just execute. We can always just take that first term and drop it straight down, and then start multiplying. 1 times negative 3 is negative 3. That's going to go underneath the next available term, which is the 0, and then we will add vertically. 0 plus negative 3 would be negative 3. Lather, rinse, repeat. Negative 3 times negative 3 is 9. Negative 10 plus 9 would be negative 1. Negative 1 times negative 3 is positive 3. Negative 2 plus 3 is 1. 1 times negative 3 is negative 3. 4 minus 3 is 1. Once I run out of terms, that last one represents my remainder. But I'm not done until I answer the question. I took the variables out in order to figure out the answer. Once I'm ready to present my answer, put the variables back. Remember though that division has an effect. I started with x to the 4th. I divided by x. X to the 4th divided by x should be x to the 3rd. So if this represents 1x to the 4th, my answer will represent 1x to the 3rd. So when I pull down my coefficients, now notice what I did over here. That 1 I know is the remainder, so I went ahead and just set up the fraction 1 over x plus 3 because that was my original divisor. When I put the variables back in, I'm not starting with x to the 4th, I'm starting with x to the 3rd. And then it's just a matter of decreasing from left to right until you run out of variables. X to the 3rd, x to the 2nd, x, the constant term should not have a variable on it, and then the next term after that would be my remainder. So final answer, x cubed minus 3x squared minus x plus 1 over x plus 3. Now, in case you're interested, there actually is a way that you can check your answer on one of these problems using a calculator. Now, depending on what calculator you have, you may or may not be able to just type in the question, hit enter, and it spits out the answer. You would need something with a computer algebra system in order to do that, basically like a TI-89 or a TI-Inspire CAS edition, computer algebra system, CAS. Most likely, if you have a TI-83 or 84, you can't just type in the question and hit enter. This calculator is not capable of doing algebra. All it can do is arithmetic. So let's use arithmetic to check our answer. Now first I'll turn the calculator on, and then what I'll recognize is that the question is equal to the answer. So if I pick a random number for x, type it into the question, figure out what it comes out to, and then take that same number, plug it into the answer, see what that comes out to, they better come out to be the same number. So here's what I'm going to do. I'm going to do this really conveniently. I'm going to pick a random number. How about 7? What I'm going to do is I'm going to hit 7, and I'm going to store, which is this button right here, for x, and then hit enter to lock it in. So now if I were to hit the x button again and hit enter, notice what pops up is 7. I can even clear out my calculator, hit x, poof, x is 7. As long as I am working on this problem, x is 7. Now what I'm going to do is I'm going to type this problem into my calculator, x and all, because my calculator is going to pretend that x is 7. Now when I type this in, I'm going to use parentheses to put around the numerator and divide by parentheses around the denominator. So parenthesis x raised to the 4th minus 10x squared minus 2x plus 4. I'm going to close off the numerator with a parenthesis. Divided by parenthesis x plus 3. X plus 3. Close parenthesis. So now I've got the original problem typed into the calculator, and keep in mind I stored the number 7 in for x. So enter, it comes out to 190.1. What this number is not specifically relevant. What's important is that when I now retype in the next part of the problem, or the answer into the calculator, I better come out to that exact same number. So let's do that. X cubed minus 3x squared minus x plus 1. Now you may be asking why I didn't put all of that in parentheses. Well, because this isn't part of a fraction. There was no reason to put this in parentheses, but when I get to the fraction, technically the top and the bottom should individually be in parentheses. Now the top, which is just 1, single term never needs to be in parentheses. Parentheses are used to group things together. I'm not grouping the 1 with anything. So I'm just going to hit plus 1 divided by, now the denominator has multiple terms, so parenthesis x plus 3 close parenthesis. Notice I've got x cubed minus 3x squared minus x plus 1 plus 1 divided by the quantity x plus 3. So that x plus 3 only pertains to the 1, which is what I want it to do. So when I hit enter, it better come out to 190.1. It does, so I can be comfortable that my question and my answer are equivalent. So as you're working on homework, as you're working, say, on a test, if you want to check to see if your answer came out correctly, use that little store feature, plug in some random number for x, type in the question, type in the answer. If they come out to be the same number, we're good. Let's move on. All right, here's another one. Why don't you try this one on your own? You can pause here, hit play when you're ready. Now, as you're going through the setup, I might recommend go ahead and set it up and then hit play to see if you set it up correctly, and then pause again once you're ready to continue. So we'll set up my structure. Remember, on the outside goes the root of the denominator, which is going to be positive 2. And then on the inside, I'm going to put the coefficients of the numerator. Now hopefully you notice that I've got several missing terms here. I start with my cubic term, but then I'm missing my quadratic, my x squared term, and my linear, my x term. Cubic should have 4 terms altogether. I only have 2. So I'm going to put zeros as placeholders. So I've got 2 for my x cubed, I've got 0 for x squared, I've got 0 for x, and I've got negative 16. 2x cubed plus 0x squared plus 0x minus 16. Now I'll continue the process. Drop down the 2. We'll multiply. 2 times 2 is 4. We'll add. 0 plus 4 is 4. 4 times 2 is 8. 0 plus 8 is 8. 8 times 2 is 16. Add that together and we get 0 as our remainder. I started with a cubic divided by a linear. X cubed divided by x should give me x squared. So this will end up being 2x squared plus 4x plus 8 plus 0 over x minus 2. Now, of course, since my remainder is 0, there's no need to write the fraction, so my final answer will be 2x squared plus 4x plus 8. All right, moving on, let's try another. Feel free to go ahead and give this one a try. Pause here, play when you're ready. All right, setting up the basic structure. Set the bottom equal to 0. Now on this one, when I solve this one, I should be getting a fraction. There's nothing wrong with fractions. Stop being afraid of fractions. So I have negative 2/3. Coefficients of the inside, 3, 5, 8, 7. No missing terms, so no need for a placeholder. Start by dropping down the 3. We'll multiply 3 times 2/3. You're welcome. I set this up nice and neat for you. 3 times 2/3. 3 times 2 is 6. 6 divided by 3 is 2. In other words, 3 times blah over 3. The 3's cancel out. You're left with the 2. Don't forget about the negative though, so negative 2. 5 minus 2 is 3. You're so very welcome. 3 times negative 2/3 is still negative 2. 8 minus 2 is 6. Now 6 times 2/3. Now of course we could do it the easy way. 6 times 2 is 12. 12 divided by 3 is 4. Or we could do it the easier way. 6 divided by 3 is 2. 2 times 2 is 4. So don't forget the negative, negative 4. 7 minus 4 is 3. Now keep in mind we've run out of terms, so that represents my remainder. Now at this point, you may have presented your answer as 3x squared plus 3x plus 6 plus 3 over 3x plus 2. And if you did that, congratulations, you followed the synthetic division algorithm, but that is the incorrect answer. Because if you remember, this problem was the one that we actually started with earlier. This was the very first one that I did with polynomial division, and I showed you the long division method, and this was the answer we got. 1x squared plus 1x plus 2 plus 3 over 3x plus 2. So looking at what we did here, notice the remainder is correct, but the rest of it, 336, should be 112. Now let me explain what's happening here. The key is this number right here, that 3. All right, that's what's different here. When I looked at the previous two examples, example A and example B, feel free to go back and look at them in your notes. You'll notice that there was no leading coefficient in the denominator. And that's what your Algebra 2 teacher may have told you. If there's a leading coefficient in the denominator, you have to use long division. If there is no leading coefficient on the denominator, feel free to use synthetic division. Now, I am here to tell you that synthetic division still works, but not on its own. We still have more work to do. The synthetic division process gets us mostly to the answer, but there's an adjustment that we have to make. The key is remembering that synthetic division technically only works when the leading coefficient is 1. So let's make it 1. Let's factor out the 3. But then you might say, but Mr. Scholar, I can't factor out the 3 because that 2 doesn't have a 3 that could be factored out. Pshaw. Here's me factoring out the 3. Remember that factoring is the same thing as division. When you factor something out, what you're really doing is dividing the original thing by that which you are factoring out. So when I divide 3x by 3, I'm left with x. When I divide 2 by 3, I'm left with 2/3. Notice if I redistribute 3 times x, 3 times 2/3, I get right back to my original. This is always possible, but rarely is it useful. In this case, though, recognize that negative 2/3 didn't come from the 3x plus 2. It really came from just this guy, the x plus 2/3. So when I divided out that negative 2/3, what I really did is I divided out this factor x plus 2/3. Notice what's still there on the bottom. We still have a 3 that we have yet to divide. So what we'll do is we'll go ahead and finish up this problem by dividing by that 3. But you got to be careful. That extra bit of division that we do only applies to these terms. It does not apply to the remainder because remember, the remainder is that which remains. It's that which does not fully divide. So leave that remainder alone. Don't divide everything by 3. Only divide the quotient by 3. So 3, 3, and 6 divided by 3 would give us 1, 1, and 2, which is the answer that we expected. When you have a leading coefficient in the denominator, go ahead and do the synthetic division process, but then finish it up by dividing by that leading coefficient. Divide the coefficients by that leading coefficient to get your final answer. Don't touch the remainder, just divide the quotient. Here's another one for you to try on your own. Pause here, play when you're ready. So setting it up, 2x minus 5 equals 0 becomes 5 halves. I have no missing terms, so 8, negative 10, negative 28. Drop the 8 down to prime the pump. 8 times 5 halves. I'm always going to do the division first to make it easier. 8 divided by 2 is 4. 4 times 5 is 20. 20 minus 10 gives us 10. 10 divided by 2 is 5. 5 times 5 is 25. 25 minus 28 would be negative 3, which is my remainder. But because I had a leading coefficient, I'm not done until I take the 8 and the 10 and divide it by 2. That becomes 4 and 5. So my final answer would be 4x plus 5 minus, because it's a negative, minus 3 over 2x minus 5. Final answer. Now up to this point, you may have noticed something. All these problems are dividing by linear polynomials. The denominators of all 4 of these problems have been linear on the bottom. So what happens if I have more than 2 terms on the bottom or higher than a first degree polynomial? Well, let's look at the next couple of examples. Now I'm going to start with one that is still binomial, and then the next one after this will be a trinomial. But I'm here to tell you synthetic division always works. In this case, this is another situation where your Algebra 2 teacher may have told you if it's not linear, if it's leading coefficient other than 1, use long division. Synthetic division still works. Here's the key. Synthetic division only works on linear factors. Synthetic division only works on linear factors. Okay, so take x squared minus 1 and break it into linear factors. X squared minus 1 is really x plus 1, x minus 1. You can kind of think of this as if I had to do, let's say, like 80 divided by 10. All right. Obviously, 80 divided by 10 is going to be 8. But instead of doing 80 divided by 10, it would be perfectly fine to break that 10 into 5 and 2. 5 times 2 is 10. 10 is 5 times 2. This is the same problem. And then instead of doing 80 divided by 10, I could divide one at a time. So instead of 80 divided by 10, let's say I do 80 divided by 5 or 80 divided by 2. It doesn't matter which one we do first. I'm going to do 80 divided by 2 because I think that's easier. 80 divided by 2 is 40. But my answer is not 40 because I haven't divided everything. That 5 is still there in the bottom. So now 40 divided by 5, well, that's going to be 8, which is the same answer had I just divided in one step anyway. My point is, when you have a large denominator, it's perfectly fine to break it up into smaller pieces by factoring and then divide one factor at a time. So x squared minus 1, difference of squares, is x plus 1, x minus 1. So now let's divide one factor at a time. Now, it does not matter which factor you start with. You can divide in either order, you will get the same answer. I have no idea which one I started with. Let's find out together. Apparently, I started with this one right here. X plus 1 produces negative 1 as my root, and then I'll sprinkle in my coefficients. 4, negative 3, negative 4, positive 3. Bring down the 4, 4 times negative 1, add and multiply, add and multiply, add. Notice on this one, I got 0 as a remainder. A little secret, don't tell everyone, this is just between you and me. On these problems where I've set it up so that you have to factor the denominator and divide multiple times in a row, I'm making this super easy for you. It will always come out to 0 as one of your remainders. The reason for that, if 0 is not the remainder, this problem gets way more complicated. Still possible, but way more complicated. So again, just between you and me, this will always be 0 on the problems that require factoring the denominator. You're welcome. So we've divided out x plus 1, but what's still there is x minus 1, which means we didn't need to divide again. Now keep in mind on that 80 divided by 10 problem, I did 80 divided by 2, which was 40, and then I didn't go back to the 80 to divide by 5. I started with the 40 and divided by 5. So I'm not going to go back to the original to divide out the next factor. I'm going to start from here, 4, negative 7, 3, and I'm just going to set up another level of my division problem right below the first one. So now bring down the 4. 4 times 1 is 4. Add, multiply, add. Now at this point, I could keep going. 0 times 1 is 0, 0 plus 0 is 0, but because I know it's all going to be zeros, I'm going to go ahead and stop here. And now for the answer. Keep in mind, this 4 represented x cubed. And each time you do synthetic division, you're going to drop a degree. So this 4 represents x squared, which means this 4 represents x. So I'm going to have 4x minus 3, and since I'm out of variables, that means this guy right here would represent the remainder, and since the remainder is 0, my final answer would just be 4x minus 3. Now that we've got that under our belts, here's another one. Try again. Pause here, play when you're ready. So the first thing I notice is that the denominator is not linear, which means it needs to be factored into linear factors in order to do synthetic division. Factors of -6 that add to -1 would be -3 and +2. -3 times 2 gives us -6. -3 plus 2 gives us -1. So this would factor into x minus 3, x plus 2. I can now set up my synthetic division. Again, it absolutely does not matter which one we start with. I encourage you to do this problem twice, one starting with x minus 3 and the other one starting with x plus 2, just to demonstrate to yourself that it does indeed come out to be the same answer. I'm going to start with x minus 3 producing +3. Numbers on the inside go up top. Prime the pump. Multiply, add, multiply, add, multiply, add. Hey, look at that. It came out to 0. That's interesting. I wonder if I set it up that way. Once I've got the first factor dealt with, move on to the second factor. X plus 2 becomes a -2. Prime the pump. 2 times -2 gives me -4. Add, multiply, which of course I don't need to do because it's all going to be zeros. So 0 represents my remainder. Final answer, if I started with a cubic, this is quadratic, so this is 2x minus 1. And there we have synthetic division. We had a couple examples where the denominator was pretty simple, where the leading coefficient was 1. We had a couple of examples where the leading coefficient was not 1, and we now know what we need to do in those situations. And we had a couple examples where the denominator was not linear. In those situations, we have to factor it out into linear before we start dividing. If you want to pause here and go start your homework just to practice this a little bit before moving forward, go right ahead. Otherwise, let's go ahead and move forward and talk about the remainder theorem and the factor theorem, which really aren't that complicated and also give you an opportunity to practice synthetic division a little bit more. So let's start with the remainder theorem. Now, both the remainder theorem and the factor theorem are pretty straightforward. And they're theorems that you probably could have figured out on your own without me pointing them out, but you know, it's my job to point them out, so that's what I'm going to do. The remainder theorem. Consider all the way back to the beginning the way we set up an answer. If I have some function being divided by some divisor, in this case I'm going to structure it as x minus a, similar to those simpler problems, example A and example B. I'm going to get some quotient and I'm going to get some remainder. No idea what the quotient is, no idea what the remainder is, no idea what I'm dividing by or what I'm dividing, just basic structure here. Now, just to help us out with some calculations, I'm going to clean this up a little bit. Notice I've got fractions on either side of my equation. I don't like fractions. I'm going to multiply everything by that denominator, x minus a. By multiplying by x minus a, that's going to cancel out the x minus a right here. And then on the right side, keep in mind there are multiple terms, so I have to distribute. X minus a times this, x minus a times this. When I multiply q of x times x minus a, it's just going to be q of x times x minus a. But when I multiply r over x minus a, the x minus a is going to cancel out. So I end up with this structure right here. F of x equals x minus a times q of x plus r. I do this so that I can do this next thing. What if I plug in a for x? What would happen if I evaluate the original function at a? Well, what would happen on the right side is that a minus a, well, that's 0, and 0 times anything is 0. So if I evaluate f of a, it's just going to spit out r, the remainder. So what I'm saying is, if a polynomial f of x is divided by x minus a, so in other words, I'm dividing something by something else, the remainder of that division problem is f of a. If I want to figure out the remainder, I can just evaluate what f of a is. Or more importantly, why is this useful? If I want to evaluate the function, I can just figure out what the remainder is. Instead of, if I give you some really ugly function and ask you what f of 7 is, instead of actually plugging in 7 to that function, I can just use synthetic division and look for the remainder. Now it's arguable, maybe it would be easier just to plug it in, maybe it would be easier to use synthetic division. What I'm saying is when the function is really long or really ugly, synthetic division is typically a lot simpler. You don't have to worry about any order of operations, you don't have to worry about any exponents, it's just multiply and add, multiply and add, multiply and add. For example, given this function, f of x equals 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18, evaluate f of negative 2. One option, of course, would be to take the negative 2 and plug it in anywhere I see x, replace it with a negative 2, and then follow the order of operations to evaluate the function. Absolutely, that is always an option. What I'm telling you is that the remainder theorem says that another option is to use synthetic division. I'm going to put the coefficients of f of x on the inside, and on the outside I'm going to put negative 2. In other words, whatever number I'm trying to evaluate, that's exactly the number that's going to go on the outside. And then follow the process. Drop the 2 down. 2 times negative 2 is negative 4. Add, multiply, add, multiply, add, multiply, and add. Again, the remainder theorem says whatever this remainder is, that is the answer to the question f of negative 2. So f of negative 2 is negative 4. And I'm sure you don't want to take my word for it. Let's pull up that calculator again. Let's go ahead and clear out my work from earlier. And then remember what I did before. I'm going to take that negative 2 and store it for x. Negative 2, store for x. Enter. Always got to make sure you hit enter to lock it in. Again, now notice x is negative 2. So let's type in 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18. And if the remainder theorem is true, then this answer should come out to be negative 4. Let's hit enter and find out. Booyah, negative 4. So I can either evaluate this one step at a time. Now, of course, if I have a calculator, obviously all of this is moot because I could just type it into the calculator and hit enter anyway. But if I don't have a calculator and I don't want to have to go through all this order of operations, I can just use synthetic division. Most likely the calculations are going to be much simpler and just pull the remainder as my answer. Alright, here are 2 more examples. Why don't you give both of these a try. Pause here, play when you're ready. Alright, first one first, second one second. So I'm going to set up my synthetic division. Coefficients go on the inside, and then the 2 will go on the outside. Drop down the first term, multiply, add, multiply, add, multiply, add, multiply, add. So I get 0 as my remainder, so f of 2 is 0. One more. Set it up. Hopefully you notice this time I have missing terms. X to the 5th and x to the 3rd and x to the 1st are all missing, so I need 3 zeros as placeholders. And then on the outside I'm going to put a 2. Drop the 1. Multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. G of 2 is 14. The remainder theorem. One last step. The factor theorem. Now the factor theorem is even way more obvious than the remainder theorem. The remainder theorem, you may not have thought that one was obvious, but this one you better think is obvious. The factor theorem. Consider 20 divided by 4. If I do this the long way using the division algorithm, obviously it's going to come out pretty straightforward with a remainder of 0. In other words, 20 divided by 4 is 5, which you already knew, but what I'm trying to get at here is that 20 is 4 times 5. In other words, 4 is a factor of 20. If I divide and I get 0 as a remainder, what I'm saying is that that number is a factor of the original one. Now, of course, I could also say that 5 is a factor, but what I'm trying to emphasize here is that if I take a number and divide by a second number and the remainder is 0, that second number is a factor of the first. On the other hand, 20 divided by 3. If I try to do the division algorithm here, I'm going to get 2 as my remainder. So in this case, my answer would be 6 plus 2 over 3. So 3 is not a factor of 20. This is me stating things that you already know. If you divide and get 0 as a remainder, then that means that which you divided by is a factor of that which you divided. If you get something other than 0 as a remainder, then it's not a factor. In terms of polynomials, a polynomial function f of x has factor x minus a if and only if f of a equals 0. Notice what I'm doing here is I'm combining the remainder theorem with the factor theorem. If I'm telling you that f of a is 0, what I'm really telling you is that the remainder is 0. Remember that by the remainder theorem, the remainder and f of a are the same thing. So if the remainder is 0, then x minus a is a factor. If x minus a is a factor, then the remainder is 0. If f of a is 0, then x minus a is a factor. If x minus a is a factor, evaluating the function at a should produce 0. Let's look at 3 examples of that theorem. You're presented with a factor, a possible factor, x plus 2 or x minus 2 on the second 2 examples, and the question is x plus 2 a factor of this polynomial? If I want to know if it's a factor of this polynomial, really, I just need to know what the remainder is. Because if the remainder is 0, then x plus 2 is a factor. Now, of course, another option is I could evaluate the function at -2. If I'm able to evaluate the function at -2 and the answer is 0, then yes, x plus 2 is a factor. So you can either evaluate the function or you can do synthetic division. It's up to you. But I will point out that you have seen these before. Hint, hint, nudge, nudge. These are the same 3 polynomials that we did on the remainder theorem, which means you've already evaluated. So looking at the first one, f of -2, when we did it previously for the remainder theorem examples, we got -4. The fact that I get -4 means no, x plus 2 is not a factor. In order for it to be a factor, this would have to come out to 0. On the second one, remember we already did the synthetic division. We came up with f of 2 equals 0. Since it's 0, I can say yes, x minus 2 is a factor. And lastly, g of 2 was 14. Therefore, no, x minus 2 is not a factor of g.